Hi, so in this video we will discuss different forms of regression models containing natural log as at least one dependent or independent term. So the first type of the model to discuss is the log-log model. Log-log means natural logarithm, and we call this type of models in this way because both the dependent and independent variables are expressed as the natural logarithms of the original variables. So this model has a very interesting property. So you probably know that we calculate elasticity of y with respect to x using the following formula. So derivative of y with respect to x divided by the ratio of y to x. In simpler words, we divide marginal function by the average function. So elasticity is free of units of measurement. So basically elasticity tells you by how many percent y will change if we increase x by 1%. So this is the measure of responsiveness of y with respect to x. So from this model we can interpret beta 1 here as the derivative of dependent variable logarithm of y with respect to the independent variable logarithm of x, as usual, by the way. And the interesting thing, I will not present proof in this video because it's not about econometrics, it's about your knowledge of math. And the interesting thing is the value of this derivative is exactly equal to this expression. So if you take the derivative, calculate and simplify, then you will basically get this expression. So from this we can conclude that beta 1 is equal to elasticity of y with respect to x. And this is how we interpret the value of beta 1. If x increases by 1%, then y will change by beta 1%. If beta 1 is equal to 5, let's say, then increase in x by 1% will result in 5% increase in y. I would like to underline that in this case we say percent, not percentage point. This is very important because in this case we analyze relative change of the dependent and independent variable. Okay, so now let's discuss something a bit more interesting, namely the application of this kind of model. So what you can see here is the formula of the gravity model of international trade. It's called gravity model because it's very similar to Newtonian equation of gravity. When you measure gravity depending on the weight of two bodies and distance between them. Weight of two objects and distance between them. So in our case, we assume that international trade, volume of international trade between countries I and J, is positively dependent on the product of their gross domestic products, which is treated as economic weight in our case. By the way, if you're interested, GDP is not the only variable to be used as the measure of economic weight. Sometimes population is used, sometimes gross national income instead of gross domestic product. So there are many possible specifications of this model, but the baseline formula remains the same. And the volume of trade is negatively dependent on geographical distance between trading partners. Geographical distance, okay, it's very simple. You basically just measure it in kilometers. Sometimes different reference points are taken, like distance between borders or distance between geographical centers of two countries, but again, those are rather details. Okay, so as you can see, this is a multiplicative model, and probably it would be very hard to figure out how you can actually estimate this. Therefore, in order to simplify your life, you can just take natural logarithm of both sides of this equation. So we take the natural log of the volume of international trade in period t, because in our case we will use panel data. Then you have to logarithmize this side of equation as well using those formulas. So after a set of transformations, this is what you're likely to get. I would like to mention that according to this formula, there should be minus in front of distance variable, because we use this formula. The natural logarithm of ratio of a to b is equal to natural logarithm of a minus natural logarithm of b. But it's not really possible to specify this in your regression model. So you're just likely to get the output with negative beta 2 coefficient. I just mentioned this because sometimes students who are good in math have some questions regarding this. So I just want to verify that everything is correct. You can see that for distance, we do not use T index. So if we analyze trade between country I and J in period T, the same applies to GDP. Then for distance, it's just time invariant variable. So it does not depend on the period. Distance is the same in 2010 and 2011. Unless there are some major political changes, so borders are changed and so on. But usually this is not the case. That's why we do not include this time coefficient to this equation. Okay, so how we interpret the output of this model? If the product of trading partners' GDPs in period T increases by 1%, then the volume of trade between countries I and J in period T will change by beta 1%. According to economic theory, we expect that beta 1 is positive, but it might depend. That's why I included change, not increase. If the distance between trading partners increases by 1%, so in this case, it means not increases over time, but rather in situation when we shift from one trading partner to another trading partner. So this is like cross-section comparison, not time series comparison. Then the volume of trade between them will change by beta 2%. Something like this. Okay, so probably this is not entirely clear. That's why I would like to use some examples, as usual, to make it clearer. So in our case, we will use international trade data set from the file attached to materials for this lecture. So we are not interested in European Union dummy. We will use this variable in the next topic. What we are interested in are trade distance and GDP product. So we've already taken natural log of GDP. That's why now we will take logs of trade and distance. Okay, here we are. So of course you can specify, at least you can try to specify this model in its linear form when you analyze the dependency between trade distance and GDP product, assuming that the rate of change is constant. So here we are, and this is the output. So again, it looks pretty nice. I mean, distance has a negative coefficient and statistically significant one, and GDP product has a positive coefficient, which is also statistically significant at 1% significance level. So I would say that the output is pretty decent. So we will forget about this model for a second, and we will run another one now using the natural logarithms. So we have, sorry, my bad, yes. So this is straight GDP product and distance. Okay, here we are. Okay, so the output is still pretty similar. So, okay, it's not really convenient for you. Give me a second. Okay, maybe in this way. Okay, so the first thing you could notice is that adjusted R-square in our new model is higher than in the initial model when we did not specify natural logs, like we just used linear terms. It's not a good idea to, make this comparison for different models. But since we are using the same variables, just different model specification, it's fine. Sum of squared residuals is different as well. So as you can see, those two models definitely provide the different output. So both of those models are not very good. I mean, very few variables are included, and the sample is rather small, but those are just for the sake of training. That's why it's not really possible to see any reason for why you shall use log-log model instead of linear model in this case. So probably in our case the only explanation is that this is because economic theory tells you to do so. So as we discussed before, each econometric regression is based on some explicitly defined rigorous economic law. So if it says that trade is described by this coefficient, then you shall stick to this form of the model. And in order to estimate this in a form of a linear model, we have to take the logarithmic transformation. During our later lectures, I just cannot figure out which one according to our schedule. I will show you how to solve different problems related to the regression models. What to do if model is heteroscedastic, what to do if autocorrelation is present. So there will be more helpful examples regarding the use of logarithmization for the sake of improving models' goodness of fit and estimators' quality. Okay, so another example apart from international trade is about the demand curve. So in theory, the relationship between quantity demanded and price should be represented by the convex function. This is just due to the character of typical consumer preferences. So according to those preferences, I mean assumptions about well-behaving preferences, this is how it should look like. But again, it's rather hard to model because this is the formula of this equation. So this is the true relationship between price and quantity demanded if you want to stick to the convex shape of the demand function. However, you can easily make it a linear function if you take natural logarithms of both the variables. So you do not estimate the relationship between price and quantity demanded, but rather between the natural logarithm of price and the natural logarithm of quantity demanded. So again, this is just a trick to simplify your life, and at the same time do not violate assumptions of the model. Okay, so that was it when it comes to log-log model, and our next topic to discuss is log-linear or log-lin model. So when we discuss this type of model, then the dependent variable is represented as the natural logarithm, while independent variables are represented as linear terms. So how do you interpret the coefficients? So in our case, beta 1 will show you what is the percentage change in the dependent variable if x1 increases by 1 unit. Sorry, in our case, just x. If x increases by 1 unit. So y is represented by the natural logarithm. Dependent variable is represented by the natural logarithm of y. That's why this variable will change in percent. We will analyze relative change. But x is represented by a linear term. That's why we will just analyze the absolute change. So if we still assume that y stands for the volume of international trade and x stands for distance, beta 1 will show you by how many percent the volume of international trade will change if distance increases by 1 kilometer. Because this is what absolute change is all about. That's why we consider the original units in which those variables are expressed. And the final thing is lin-log model. In this case, the dependent variable is represented by a linear term, and the independent variable is represented by a natural logarithm. So in this case, we interpret the value of beta 1 in the opposite way. So what is the absolute change in the dependent variable reflecting relative change in the independent variable? If y stands for the volume of international trade and x stands for geographic distance between two countries, then beta 1 will tell you by how many US dollars y will change if x increases by 1%. Okay, I really hope this was clear when it comes to log-log, lin-log, and log-lin models. In the next video, we are going to cover reciprocal logarithmic model and polynomial model, and I really hope you enjoyed this one.